Hello and welcome to this AWS webinar. My name's Ian. I'm a technical evangelist with Amazon Web Services based here in Europe, and I'm going to be your host for the session today. If you've got any feedback on the session as we continue, feel free to send me a tweet during the session and I'll reply to you immediately afterwards. This webinar is one of our Masterclass series webinars. I guess some of you may have attended this series before, but just to quickly recap, the Masterclass series is really intended to be a technical deep dive which will take you beyond the basics on one specific AWS service. Okay, so we're going to spend about 45 minutes here and we're going to try and educate you on how to get the best from a specific AWS technology, show you a little bit more about how things work with that specific service and how you can get things done. We do also have another series of webinars called the Journey Through the Cloud series, which you should be receiving email about if you received a notification email about this webinar. The Journey Through the Cloud is slightly different. That's a sort of solutions-orientated webinar, which will focus on particular IT or business challenges and how you can apply a variety of AWS services to solve a particular challenge or address a particular scope area. So if you're interested in a more broad look at AWS services, then you might want to try to get along to one of the Journey Through the Cloud webinars that we're also running. We're running one in the next couple of weeks, which is to do, for example, with storage and backup options on AWS. So stay tuned for that if you're interested in that broader sort of look at things. Just a couple of logistical points before we start the content today. Firstly, the materials from today's webinar, they'll be available for download immediately after the session, so you can get hold of the slides, and in fact you can re-watch the webinar pretty much immediately after it's finished. If there's any areas that you want to go over again or areas that you want to re-watch in order to make sure that you fully understand what we've gone through, then you can access an on-demand recording of the webinar immediately. If you've got questions during the session, submit those using the questions button that you should be able to see at the top of the webinar as you're viewing it. I will also show you some social media links later on that you can use to get more information about AWS, and also use those to provide feedback about the webinar as well as rating us using the webinar platform. And lastly, because the topic that we're going to be covering today is a pretty detailed topic, the topic of Elastic MapReduce, EMR, I'd like to point out that we do have a solutions architecture team here at AWS that can help with follow-up on any detailed questions that you might have. So if you do submit questions and we don't answer them during the webinar today, don't worry, because a member of our SA team, our solutions architecture team, will get back to you after the webinar with the detailed answer. And of course, if you want to follow up on that, you're welcome to do so. So that's enough about resources. Let's get into the content today. So today's topic's obviously going to be about Elastic MapReduce. This is a key tool really in a toolbox that AWS provides to help you deal with big data challenges and solve big data problems. The great thing about Elastic MapReduce is it makes possible analytics that might not have been previously feasible, either for performance or cost reasons. And the way in which Amazon have wrapped the Hadoop engine, which is the core of the EMR service, in a framework, makes it very easy to run Hadoop, to do that on demand, and to do it with a lower cost profile than that which you'd typically see if you were building and operating your own Hadoop environment, either in your own data center or in another sort of dedicated environment. So it's a pretty powerful tool, and we provide a broad ecosystem of tools with Elastic MapReduce that can help you handle specific use cases, and we're going to explore a couple of those tools in that ecosystem later on in the course of the webinar today. So first of all, let's do a quick review. What exactly is EMR? Well, as I've already said, it provides Hadoop as a service. So Hadoop is a tool for processing data using parallel computing techniques. The core of it is really something called MapReduce, an engine that enables you to map and aggregate data in a two-step process. And you can put on top of that a set of tools that enable you to use query languages on top of that parallel framework. And the parallel framework provides for what you can probably best describe as near linear scalability. So the more compute horsepower you throw at your problem, the more rapidly your problem will be answered, or your data will be processed, and you'll get the results that you've asked for. And obviously, with that performance scalability, cost scales in a linear way as well. We've done a lot of work at AWS to integrate EMR with other AWS services, EC2, the compute service, which forms the core of EMR, and also storage services like S3, DynamoDB, and some new services which we'll come to talk about later in today's webinar. And as we've already said, we provide this cost-effective wrapper around Hadoop, which makes it very easy to execute analytics or data processing tasks in a timely fashion, much more easily than building your own cluster. So that's what EMR is. And as we've said there, it's really a framework. It splits the data that you're going to process using Hadoop into pieces, and it lets processing occur, and then it gathers the results of that and returns those results to you. And let's just walk through precisely how that works. So taking a very common example, which might be, say, clickstream analysis or web server log analysis, you're going to have a very, very large log file which can be generated from high amounts of traffic on a web property. That might contain a set of actions that you want to identify for one specific user. What you can do with EMR and with Hadoop more generally is to split that log file into a great many small pieces depending upon the number of nodes in your cluster. Those small pieces will then be distributed to the nodes that you have available to them and processed, and then Hadoop will aggregate those results back together from all of those nodes, and you can use that obviously to work out precisely what John Smith or some other individual did in the course of their interactions with your website or your application or whatever it is you happen to be logging. So by achieving that sort of parallelization effect, you can process that data much more quickly than you can with a small cluster or even with a traditional sort of single powerful machine approach, and you can get your insights a lot more quickly. And it's particularly useful for integrating that sort of analytics process into some sort of regular batch or workflow-based task where you want to scale up and scale down, or scale in and scale out, I should say, the computing and processing resources that you're going to throw at the challenge in order to reduce the time that it takes you to get insight from your data. So that's what EMR is all about, really, is managing that process of distributing a task across a number of different processing or compute nodes, executing the task, and then consolidating the results together and giving you your information back. Now, there's two core components of Hadoop. This is the Hadoop logo that you can see on the slide here. There's two core components of that. One is HDFS. So this is the Hadoop file system. It's the mechanism that Hadoop uses to enable you to store your data across the cluster of nodes that you're going to be creating as part of your cluster, placing that data close to the computation resources that you have in your EC2 nodes. And it's reliable, and it can deal with data protection as well. So this allows you to, for example, deal with node failures during the course of the lifetime of your cluster without losing any of your data. The second thing that you have as a core component of Hadoop is something called MapReduce. Now, this is the framework that enables you to perform data analysis on your data and then aggregate the results. And we're going to talk a little bit more about how MapReduce works and what some of the interfaces to MapReduce are later on in the webinar today. But before we do that, let's just take a quick step back up a little bit and talk about big data more generally and some of the other sort of peripheral tools that AWS can provide to help you ingest and deal with your data. So it's a pretty good slide. And this is the only joke of the webinar, by the way. We can say that big data is not Hadoop. Big data is bigger than Hadoop. And there's a lot more parts of the ecosystem that are important. And many people consider the definition like this. So it's the volume, in other words, the speed, in other words, the size of the data set that you're dealing with. It's the velocity, in other words, the speed at which your data set is growing. And it might be the variety of data that you're dealing with. If you want to join data from a variety of different sources together, that could cause you to think of it as a big data challenge. But there are also other definitions that people might say makes a data problem into a big data problem. One example of that, for example, might be you're dealing with data in large volumes, but data that has low density of information in it. And a good example of that might be things like processing streams of data from social media like Twitter, where you've got obviously a massive volume of data flowing through the system, but only a certain small percentage of that might be relevant to the query that you want to run or the business problem that you're trying to solve. And you need to sift through that data in order to find data which has relevance to your challenge. So that can be, I guess, a fourth sort of definition for big data. How we generally consider it is that it's wherever you need to innovate in order to deal with your data. So if you've got something which makes your data difficult to collect, to store, to process, or to analyze in order as a result of one characteristic of your data or more than one characteristic of your data, then that might make you consider it a big data challenge. And we're going to look really in this webinar at the analyze phase of this process. But before we do that, let's just look at a few tools that can help you get data into AWS so that you can work with it using EMR, and also some technologies that we have that can help you deal with storing data once you have it inside AWS. So here we're looking at ingest techniques that you might use. There's a few different things on this slide here which I'll just quickly talk through. So mechanisms for getting large amounts of data into AWS so that you can process it with EMR and with other tools. Well, the first thing that customers use is they use something called Direct Connect. Now this provides for a low latency, high bandwidth connection directly from your facility or data center or network straight into an AWS region via a Direct Connect peering point. If you're in the UK, we have one of these in London, in Telecity, in Docklands, where you can bring your network, connect to the AWS Direct Connect network, and then benefit from this high bandwidth, low latency connection to our region in the EU West in Ireland. So that's a technique that many, many customers use, particularly customers that want to constantly stream data in real time or near real time into AWS for processing, but they want to do that off the internet on a network which has more certain performance characteristics and could be considered more secure or at least private. So that's Direct Connect. Second option that you've got is something called AWS Import-Export. This is pretty unusual from many customers' perspective. It's still a truism that one of the highest bandwidth transport mechanisms in the world for information is a VAN, and this involves customers putting their media, it's normally hard disks or USB drives, in the back of a courier, FedEx or some other courier, sending it to our region in Ireland, where we will connect the media to our systems and allow you to load the data from there. So that's actually used by very many customers, believe it or not, particularly those customers that are sending huge volumes of data and are doing that under a sort of batch process. So looking to customers there in life sciences or genomics, it's pretty common for customers to use import-export for that kind of repeated process, but also common for customers that are onboarding a large volume of data at the beginning of their use of EMR or other analytics tools within AWS to use import-export as a mechanism for getting their information into one of our regions where they can then obviously get it adjacent to the compute and storage resources that we provide, and take advantage of the power that we can provide to help them process that. So that's import-export. The third option here is very new. We only announced this in November last year at reInvent, and we've now got quite a few customers using this. This is Amazon Kinesis. So this is a highly scalable stream processing service for record and event buffering. So you post your events into a Kinesis stream, which is elastic and can be scaled in response to the amount of throughput that you feel you're going to need. Those events will be delivered in a time series ordered manner into EMR using a technique that we're going to talk about later. And that can be used for quite a wide variety of different application types. So you're talking here about IoT applications, Internet of Things applications, where you might connect sensor networks to Kinesis and use that as a mechanism for gathering data from a distributed network of sensors. You can use it, for example, as an instrumentation endpoint within applications. So we have quite a number of mobile app developers that are using Kinesis as a mechanism for getting analytics out of their applications whilst they're being used. So this is used, for example, by a customer called Supercell in the Nordics that produces very successful mobile games. They use Kinesis to gather events from those games while players are using them and perform analytics actions on the basis of those activities. So it's a very scalable mechanism for getting large volumes of small events into EMR or into other data storage options that we may have. And then lastly on here, Amazon Storage Gateway. So this allows you to synchronize local storage to the cloud. It's a real good tool if you've got existing ETL workflows where you might simply write files into a block device. You can write them onto a block device provided by the Amazon Storage Gateway, and that information will find its way into Amazon S3, where you can later access it from EMR. So a very good tool to use if you want to integrate Amazon services and EMR specifically with existing ETL or data pipeline workflows that you might have on your own premises. So that's ingest. Let's just touch quickly on storage. So once you've got your data and you want to get it up into AWS, where do you store it? And there's a few different options for that as well. Probably the anchor and the one that we'll be discussing most extensively during this webinar is S3, which you can see on the right-hand side there. That's an object data store, which I'm sure many of you will be familiar with. It provides for 11 nines of durability, which is a very, very high degree of durability. Your data only resides within the region that you place it in. So if you place data into an S3 bucket, which is located, say, in Ireland in the EU West region, your data will not leave that location unless you move it. So it can be good also for compliance and data sovereignty requirements that you may have to keep data in specific locations. But the main characteristic, of course, is you can store an unlimited amount of data in there in up to 5 terabyte object chunks with that very, very high degree of durability. So it's a super reliable place for you to put your information adjacent to the compute resources that you're going to build your EMR clusters out of, where you can access it very quickly and be certain and secure that the data will be there when you need it. And then some other data storage options. RDS, the relational database service. So we have several options here: PostgreSQL, MySQL, Oracle, or Microsoft SQL. Tools that enable you to quickly and very, very easily start and access a managed relational database service, where you might store, for example, structured output that you're going to create using an elastic MapReduce job, and we'll talk more about that later, and some of the tools you can use for interfacing between Hadoop and structured data sources. And then lastly, DynamoDB, a NoSQL schemaless provision throughput database that we have. Very, very high performance and very, very consistent performance. And if you are streaming from Kinesis, for example, you may place records into DynamoDB that you need to access very quickly, and also integrate that data with jobs that you're going to run on Hadoop, for example, in the form of joins. So a tool that you can use to support in-app high-performance data access, as well as integrate with EMR if you need to do so. So that's a quick tour of ingest options and storage options. Now let's get started with a more involved discussion of what EMR is, how it works, and how you can use it, of course. So there's basically 3 steps, and you'll see this diagram if you look at the EMR console, which we're going to talk about quite extensively later in the webinar today. So this is part of the EMR console, which just outlines what the things are that you need to do in order to execute an EMR job. So the first thing to do is get your data and your processing application and upload that to S3 for storage. You can use the other storage methods that we've talked about, but S3 is probably the de facto that you're going to start with. You're then going to create your cluster using either the console or the CLI, and you're going to specify things like data inputs and outputs, the parameters of your cluster, the security settings that you want, etc. And then once your job's running, whilst your job's running, perhaps I should say, you can monitor the health and progress of your cluster, and you'll be able to retrieve the output when your cluster's completed from S3. So, what are the different node types that exist within a cluster? So at its core, the framework enables you to start a cluster running Hadoop using, as I said, the console or CLI tools. And those CLI tools are actually built using Ruby, and they form a wrapper around the AWS API for EMR. And we'll take a look at some of those tools in a little bit more detail later on in the webinar today. So what happens when you start that cluster? Well, the first thing that happens is you're going to have this master instance group created. The master instance group, essentially, this controls everything that goes on inside your EMR cluster. It coordinates the tasks that the other nodes will do. And you'll find that that master instance node runs MySQL in a self-contained installation, which happens as part of creating your cluster. And that basically coordinates the jobs that you're going to run on your EMR cluster, and handles, for example, the transfer of data from S3 into the nodes that are going to be executing your task, and gathers up and aggregates the results that you have. Once you've got that master instance group created, the next thing that happens is a core instance group will be created. This contains, again, a number of EC2 instances, and you cannot shrink this. So when you create your cluster, it's important to have a decent appreciation of what your the minimum size of your cluster needs to be. Once you've defined that core instance group, it will run for the lifetime of the cluster. You can add to it, but you can't reduce it below the initial starting value. So that's an important performance characteristic, performance parameter rather, that you just need to bear in mind. And that core instance group will run for the lifetime of the cluster. These instances have the HDFS file system on them, and they're Hadoop data nodes in Hadoop speak. And they also run something called the Task Tracker daemon, which is the piece of software that actually does the job that you're asking the cluster to do under the control, in this instance, of that master instance group. So that's where your data lives. You can also define an optional group called a task instance, and this can be resized in terms of the number of the nodes during the lifetime of the cluster. These nodes only run the task daemon. They don't provide HDFS, and the master instance group coordinates them. It takes data stored in HDFS on that core instance group, passes it to this task instance group that will process that data, and then they'll pass the results back to the master node. So that master node basically coordinates things, pulls the data in and out of S3 as required, as you can see here. So it's talking to the core instance group and the task instance group, assigning data. It's gathering the data from S3 and placing that either into the core instance group if it's going to be stored on HDFS, or into the task instance group if it's required for a processing task, and it coordinates pushing that data back to S3 when it's finished. So next let's take a look at the map and reduce functions. So how does this idea of splitting the job across a large number of nodes actually work? Well, let's take an example here where we're going to have a look for records of a specific type in a file which has been split across a large number of nodes. So this is a single node example where you would take that input file, you would map it, in other words, extract the records that match a particular type, and place those into output files, making them available for processing. When you scale this out into a multi-node environment, you have this sort of model where your input file is split across a number of different nodes. Each one of those nodes performs that map function, extracting a series of records which match the different criteria that you want to then reduce down and perform your calculation on. Those records are placed into files, run through that reducer function, and placed into those files either for post-processing or to calculate a total or perform some of the calculation on that data set. So that's how that environment and that model would work. This is a very important slide now. We're going to have a look at ecosystem tools. So everything we've talked about so far has been AWS specific and AWS tools. It's very important to make the point that EMR is a pretty open environment as far as using third-party tools is concerned, and many of these are open source. So let's just have a look at an example of an ecosystem you might build for data ingest and processing. Firstly, let's just recap on those AWS tools that we've already talked about. So Kinesis, that's a mechanism, as we've already said, for streaming data directly into EMR. We actually released something in February called the Elastic MapReduce Connector to Kinesis. This allows you to stream events from a Kinesis stream directly into an EMR cluster. So, for example, you could write an SQL query using one of the query tools that we're going to talk about in a few moments against a Kinesis stream, or you could build reports that join and process Kinesis stream data together with other data sources such as DynamoDB or unstructured data that might be held in S3. So you can integrate these different AWS services together to deal with real-time data streams as well as static data sets that might be held in S3 or in DynamoDB. There's also a wide range of open source data management tools available that integrate with Hadoop and therefore integrate with Amazon EMR. A couple of examples of that are Flume, which you can see here. This is an open source log aggregator. So if you're doing large-scale distributed logging across a large number of compute nodes that might be running an application for you, you can aggregate all of that logging together, and you can stream those log entries directly into HDFS and make them available for processing via EMR. So a very common use case is to deal with massive volumes of log data using that kind of technique. HBase is a key value, an in-memory key value stored similar to DynamoDB, which can run on top of EMR. So mechanisms for boosting the performance of particular queries or particular data sets by using in-memory techniques on top of your EMR cluster. They're open to you, and there's a wide range, as I said, of different tools in that data management ecosystem that you can take a look at. Next, you have a set of analytics languages and tools that are available. And here you're looking at Hive, excuse me, and Pig. So these are tools for using query-style languages on top of an elastic MapReduce cluster. So dealing with SQL-style query construction and syntax, and being able to address tables that aren't really tables that might be mapped from text files stored in S3, but accessing those via an SQL-style language with Hive, which we'll talk more about later, or using a language called Pig Latin, and you can see the logo for Pig there on the right-hand side, which is a query scripting language that you can use to perform or to define scripts that you might perform across quite large data sets. There's also something else which isn't on the slide here, which is called Impala. This is pretty new. Support for this was announced in December last year for EMR, and this allows you to use, again, an SQL-like query language on top of EMR, but it does that predominantly in memory, so it's very, very performant, and provided you've got sufficient memory in your cluster to hold your data in RAM, you can get some very, very good performance characteristics by using Impala together with EMR, and that's fully supported by Amazon now. And then lastly, something called Scoop. So this is a mechanism for transferring results or bulk data between Hadoop and other structured data stores that you might want to run. So if you've got an environment where you want to pre-process data in Hadoop, but then make it available for structured queries, a smaller data set obviously available for structured queries within an RDS environment or another structured data environment, you can use Scoop for doing that, for efficiently transferring bulk data between Hadoop and other structured data source. So again, that's another Apache project that's fully compatible with Amazon EMR. And then once you've got your data into RDS, you can use things like AWS Data Pipeline to integrate data from a variety of sources and maybe load that into a data warehouse like Amazon Redshift for analytics, or use of dashboarding tools that you may have. And there you can see the Impala logos on this final slide as well. So that's a bit of a discussion of the ecosystem that's available to you. Let's move on now and take a look at the creation of job flows on EMR and how you might actually use EMR in order to analyze and process data. So this is the process that you'll go through when you create an Amazon EMR cluster. So you're going to create your cluster, and we'll show you how to do that in a second with a quick run through of the console that's available to do that. What will happen at that point is when you load your data into your cluster, if the data is large, Hadoop will automatically break your data set up and distribute that across your cluster nodes. If it's too large to process it quickly on a single cluster node, it'll do that. And that'll obviously improve the responsiveness of your job and allow you to access a larger pool of compute resources and achieve that linear scalability that we talked about earlier in the webinar today. You then run a series of job steps, and there's a few options on these. So these can be compiled Java files, compiled up into jars and made available via uploading them into S3 and then specifying them in the EMR interface. Or it can be a script executed by something called the EMR streamer, which we'll talk about in quite a bit of detail later on in the webinar today. And that allows you to basically process standard input and standard out using scripting, and you can use many, many different languages for that. If that's Python, it can be shell scripts, it can be pretty much anything that can deal with standard in and standard out and is installed upon your Hadoop nodes. And you can have multi-stage jobs. This is quite important. So you're basically chaining these steps together, executing subsequent steps using data from the previous step, and passing data between those steps using either the HDFS file system or S3 as appropriate. And then at the end of your job flow, when your cluster's terminated, your output data will generally be placed in S3 for subsequent use. So that's the sort of model that you're gonna see in these next few slides. Here you're looking at the AWS console. So if you go into the AWS console and you click onto the EMR section, you'll be presented with this screen We're going to show you a sort of mocked up demo here which uses a sample application which has been created. So if you go into that, you'll see at the top right hand side of the screen there you have this configure sample application button. We're going to use that to show an example of one of these stream based processing tasks. So if you click on that, you'll be presented with this menu, and there's a drop down menu that will appear there with a few different sample applications available on it. The one that I've used here to create this demo is a sample application called word count, and we'll explain to you in a second how that works. But basically, when you select that, you are asked to enter an output location for the results of this EMR job, and you have to use an S3 bucket for that. So you can see I've specified an S3 bucket there as my output location. I've also turned on logging and specified another object prefix in the same S3 bucket to hold my log data. We're using a streaming application here for this word count application. And just to quickly explain what Hadoop streaming is, as I said earlier, this is a utility that comes with the Hadoop distribution. It allows you to basically create and run map and reduce jobs with any executable or script as the mapper or the reducer. So it'll read input from standard output, and then the reducer will output the data through the standard output. And it's going to take typically text data with each line of input output representing a record, and separating those records with a tab. So you've got a sort of tab separated key value pair that you're going to be working on. And with this example application, if you scroll down to the bottom of the console, once you've been through that first step of determining your output location and where you're going to store your logging data, you'll see here the job steps that are going to be created for the job flow that's going to be executed for this sample app. And on the right hand side there, if you click that edit button, that's where you can make changes to the job flow that's going to be created. And that will take you into this window, and you can see here, as you would do in creating a customized job, in this sample application, the mapper script is stored on S3 and is being pulled down into the cluster and then executed at the point at which the cluster is created. So if you were to extend that out, you would see that that mapper script is actually a piece of Python, which you can see on these next couple of slides. So this is a word count Python script which has been used for this sample app, and you can see what this does is it basically reads standard in. It uses a regular expression to identify individual words within standard in, and it counts them and outputs basically a tab separated key value file, which you can see here, into tab delimited records. So it would say long sum value colon whatever the word is that's been identified, and then the number 1. So you'd end up with a very large file with a lot of words with the number 1 next to them. That will be the mapper stage of this particular job. And also jumping back onto that prior screen, you can see that an input location here is set. So the same thing, when setting up a custom job, you would place your data into S3 that you want to work on, as we've already said. And then you would specify the location of the data files that you wanted to be the input for your job in this wizard-driven menu here in the console. So that's the input source which is being set there. This particular job uses a predefined S3 bucket that contains these samples. So I'd really encourage you to go and run this sample task flow and take a look at both the contents of those files, which you can just download, and also the output that you get. Now, the output is again directed to that S3 bucket that we've already specified. So you can see there my output is going to be placed in this particular path prefix within, this is one of my own S3 buckets here that you can see by the prefix. So the input and the mapper comes from the demo location, the sample location, and the output would go into an S3 bucket that you specify. And in this particular example, we're using a built-in reducer script function which is called aggregate. And this aggregate function will basically sum up the key value pairs. So it's looking for matching keys, and it's adding together all the values in an aggregate for all of the keys that match one another. So running this through, you'd get this sort of output where if you had multiple text files that had within them abacus 1, abacus 1, abacus 1, you'd end up in the example I've just given with abacus 3 in the aggregate file as part of that reduce function. So that's how this particular sample application works. The next thing that you can do is you can configure hardware for your EMR cluster. So this is back into the main console screen now. You're looking at setting a hardware configuration, and you can see you can independently specify and scale actually the master, core and task nodes. So if you were to go to those drop-downs, the master, core and task drop-down, you'll see there a long list of supported Amazon EC2 instance types that you can use to build your EMR cluster. And obviously, with testing and with running your jobs repeatedly, you may come to realize that you need to optimize around a particular instance type. If that's a memory-intensive instance type, if you're going to be running Impala on your cluster, which is obviously an in-memory query engine, as I've already described, or a CPU-intensive instance type out of the C3 family. If you're going to be running particularly computationally intensive mapper or reducer scripts or mapper or reducer jars, then you may want to optimize your EC2 instance types in response to that, and you're perfectly free to do that. You can do that by changing the values in those 3 drop-down boxes there. And just a quick recap on what those instance groups do. I've already covered this to some extent during the webinar, but the instance groups, the master instance group, obviously that's the thing that manages your job flow. The core instance group, that contains the nodes that are going to run the HDFS distributed file system, the Hadoop distributed file system, to actually store your data. And they're also going to run the task tracker. So they're performing storage, and they're also performing execution processing as part of your task. And then you can supplement that with additional computation resources in this task instance group. If you've got a particularly computationally intensive flow that you want to run, then add a task instance group and put C3 or similar instances in that, and you'll have more computation resources available to you. Security and access is pretty important. So if you look at the console, you'll see a section here labeled security and access. And what you can do there is basically specify an EC2 key pair, which will allow you to SSH onto the master node for your cluster. And if you keep your cluster alive, you can run your job flow and then SSH onto the master node, and you might perform additional interactive steps. This is a common technique that's used for developing EMR job flows, where you're basically driving the cluster interactively, recording the steps that you're taking interactively, and then after you've done that, defining scripting to automate that particular flow in the future. So it's quite common for people to build up their EMR job flows iteratively, running a series of automated steps, and at the end SSHing into the master node and continuing to work with the data and work with the cluster interactively. And to do that, you would tag this bottom here at the bottom and switch off auto terminate for your cluster. So go down into the console. At the very bottom of the cluster, you'll see that auto terminate option. It defaults to yes, but if you switch that to no, your cluster will stay up. You'll be able to SSH into it to continue working on your cluster and working on your data. But just don't forget to terminate your cluster at the end, otherwise you'll continue to pay for it, quite obviously. So the output from that task that we've run will look something like this. You'll end up with an ordered sequence of words which have been run through that mapper function and then run through that aggregate function, which is that built-in aggregate function, to calculate how many times each of these words appears in what is actually a pretty large set of text files that are processed by this particular flow. So that should show you how to execute that sample job using the console. Now, naturally, like everything with AWS, the same functionality and process can be executed using the CLI. And the CLI for EMR is a Ruby-based CLI, as I've already mentioned. The slides here at the bottom, you might not be able to read it, but there's an installation guide there linked for the EMR CLI tools that you can use and follow in order to get those CLI tools set up either on a local machine or on another EC2 instance that you might use for that purpose. I use a T1 Micro to run my EMR command line tools. It's a bit easier than keeping it installed on a laptop, which can be a bit volatile. I know that system is available. I just spin it up when I need it, and I can then access and create EMR jobs as I've done here. And you can see there should be some familiarity in what you're looking at here. So basically, this is a command which replicates the execution of that sample job that we just walked through using the console. We're defining the mapper, which comes from that S3 bucket, as I've already said, and is a Python script called wordsplitter.py, which we've already taken a look at. We're defining a set of input files, which once again comes from a public S3 bucket. So that's location containing a large number of text files, which are going to be processed by that map and then MapReduce step. We're defining an output location. So in this case, we've got a fictional AWS bucket called my bucket, but you would put your own AWS bucket, S3 bucket in that location. And we're specifying once again that built-in reducer function. So that command line command sequence there would execute the same process that you've seen within that series of console shots. Now, there's some defaults that you need to be aware of here. Basically, that you will launch your job flow on a single node cluster using an M1 small instance unless you specify otherwise, and that's fine, obviously for prototyping purposes. But if your job gets large and you need to process a large number of data, which is typically what you're going to be using EMR for, then obviously you're going to need to specify a number of instances that you want to run your job on, and also maybe change the instance type that you want to use. And you can see this in this example here where we're specifying 5 instances and we're running in this case on the M24X large instance type. So a mechanism for specifying a larger pool of resources upon which you're going to execute your EMR job. You can also see here that we're specifying the alive flag as well. So this would be the same as switching off terminate on completion in the console. In this instance, we're specifying that on the console in this command line command, and that will keep running that cluster so that we can add steps to it after the event. You can also add third-party ecosystem tools to a job flow, to an EMR cluster, via the command line. And here you can see an example command that would basically add in the PIG interactive capability, add in Hive, and add in HBase, so adding additional modules into your EMR install to enable you to use those tools in your job flow. And lastly, you can also execute bootstrapping actions. So this is important if you want to customize your EMR cluster in any way, and we'll talk about what some of those customization options are in a moment on the next few slides. But you can execute those customization actions via the command line using this --bootstrap-action option, and you're then going to pull in a series of scripts that AWS makes available that can execute various customization bootstrap actions on your EMR cluster at the point at which it's created. So an example of that might be, here you can see configuring JVM properties. So here we're changing the heap size, and we're changing garbage collection time ratio as well in this particular example. So modifying parameters of your JVM in order to optimize it for a particular application, or rather set of actions that you might want to run via a compiled jar. You can also configure cluster-wide Hadoop settings, and you can configure cluster-wide memory settings. The last ones can be particularly important if you're running on memory-optimized instances, or you want to make the maximum possible use of memory on small instance types. Then use that memory-intensive option to configure that. And these are pre-canned scripts that can be pulled down from an EMR support bucket that we make available, executed on your cluster at creation time, and can tweak the parameters of your cluster. And you can do some other stuff as well. So you can run commands. So this example here shows a very, very simple scripted action that allows you to identify master nodes. You can run actions on shutdown. So this might be a mechanism for example, getting additional processed data or logs off your nodes and placing them into an S3 bucket, or triggering some other action via an API call. You can do that via shutdown actions. They all run in parallel, by the way, and they need to complete within 60 seconds, but you can configure and execute shutdown actions by doing that. And lastly, you can load and run a custom script from S3 using bootstrap action, and pulling down a shell script from S3 and executing that on your nodes as well. So you've got a high degree of flexibility to customize and tweak your cluster at create time by using those tools. The same functionality again is also available via the console-based interface. So if you look at the top of the screen here, you'll see bootstrap actions. You can add a series of Bootstrap actions by using that drop-down menu. You then be presented with some configuration options, and you can achieve the same thing that you can achieve through the command line by using that interface. And you can see here how that works. So this would be a configure Hadoop Bootstrap action, pulling down the configure Hadoop script and executing it with a few optional parameters, in this case increasing IO file buffer size. So there's several options there for customizing and configuring your environment as you need to do so. So now we're just going to move on quickly and take a look at some integrated tools. We're talking now to date, really, throughout the course of the webinar about foundational EMR capabilities. Let's now take a look at what you can do if you add in some additional tools. And reasons that you might do that. Well, Hadoop streaming, it's flexible in the sense that you have high language flexibility, but you're really limited in terms of the complexity of the process. It's basically this two-stage data flow. You're going to map and reduce your data, and if you need to join data from a number of sources, it can be pretty lengthy. And of course, if you're doing that using Java, you've got a relatively lengthy compile and deploy time, and you are having to write your analytics in a Java environment, which can be a restricted skill set in some environments. So what you tend to find is people tend to gravitate towards higher level tools that can help them get value more quickly from this kind of technology. And those include things like Hive and Pig and HBase, which you've already touched upon. I'm going to have a look at Hive here in the first instance. So a quick dive into Hive integration. Hive provides a schema on read, so it enables you to convert structured text data sources into data sources that can be queried using something called HiveQL, which is similar to SQL but has a reduced feature and function set. So you can see an example query there. It requires some setup, basically you mapping those text files, that input data, into tables within HiveQL, and it uses SERDES, so serialization, deserialization, to make it possible to query different input formats. Now, some pretty powerful data types in it that are beyond the data types within SQL. And there's a quick comparison here of SQL and HiveQL. So there's some syntax changes that you need to be aware of. There's some stuff that isn't supported in HiveQL, so transactions, indexes. It's nowhere near as fast as SQL, which is a near real-time system. You're looking normally at several minutes as a minimum to return a response to a HiveQL query, because obviously the query needs to be distributed across the nodes, mapped into the tables, in quotes, that are made available to you through that configuration step. And then obviously that data then needs to be aggregated up and results need to be returned. So it can be a lengthy process, but you can deal with very, very large data sets that will be beyond the scope of a traditional structured SQL data source. And it also has some features which don't exist within SQL, such as multi-table inserts and create table as a select. So selecting data and then automatically creating tables immediately from that, which can make it good again for these very, very large data sets. It provides a JDBC listener, so you can access data within your EMR environment using JDBC compatible tools. And there's a few things you need to do there, basically in opening up a security group, a port in the security group on your EMR master node to allow that port to be accessed remotely, and then creating an SSH channel so that you can access that from wherever you are running your JDBC query tools, which of course could now be on Amazon Workspaces if you wanted to do that. So run them adjacent to your EMR cluster in the same VPC. That's perfectly possible to do. And on the CLI, you're looking at something like this. So you can create a Hive job flow. You're basically specifying Hive scripts, which you once again going to store within S3, specifying those on the command line, and then performing this mapping step. So you can create an interactive session. And then you're going to perform this mapping step. So this is basically where you would point your EMR cluster at an external table. So this is a mapping to a set of source data which is stored in S3 in this particular instance. The data obviously needs to be in the right structure. So you're looking at tab delimited data in that external data source. And here we're going to map in from this location on S3. So grabbing that data source from S3, mapping it into a table within Hive, and then once you've done that, it's available to perform HiveQL queries on that data. So here we would select star from impressions, limit 5, and that will be selecting from a data source directly via Hadoop, even though that data source is actually a text-based set of text-based files stored off in Amazon S3 and mapped in using that configuration step. So that should give you a quick flavor of how you can use HiveQL for interactive queries. And here's a quick summary of comparison between different data sources that you might use within EMR. Okay, so let's move on now to look at some cost considerations before we close. So this is really important. So there are some techniques that you can use for optimizing cost when running Hadoop jobs on EMR on Amazon Web Services. And this is one of the main reasons and one of the main benefits that customers get from using EMR as a platform for their Hadoop workloads. So this is the main point, really, that you can parallelize on Amazon. So if you were going to run one instance for 100 hours, it would cost you the same as running 100 instances for 1 hour. So you can very, very quickly spin up, get access to large farms of compute resources, and then discard them when you're finished with them. And also, the cost of running instances is pretty low. So, for example, if you're going to run a small instance, 100 small instances for an hour, that costs you $8. So it's very, very low cost. And naturally, you can scale it up as your workload gets bigger. So if you want to run 1,000 instances, again, you can run those 1,000 instances for an hour for just $80. And again, 1,000 instances for 1 hour costs the same as one instance for 1,000 hours. So you can devote large amounts of compute resource to tackling big data problems using Hadoop with EMR, and you can do that very, very cost effectively. You can further improve your economics for running EMR jobs if you consider a blend of different instance types, and we talk about this pretty extensively in most of our webinars. But the lowest cost way to acquire compute resources from AWS is to use reserve capacity. So if you know, for example, you're going to have those core instance nodes running permanently because you're going to permanently store data in HDFS, and you want to use those core nodes continuously as part of some sort of job flow that you're going to access repeatedly as part of an application or workflow. You can pre-provision that capacity using reserved instances, and it will significantly lower your costs. And if you want to add additional capacity for particular large jobs at certain parts of the week or month, you can do that using on-demand resources, and you can even infill with the spot instance type to further improve your cost base and reduce the cost of running these jobs. And the spot market is quite an interesting tool for running EMR. So here you're looking at a spot pricing history, and you can see that the spot price for this T1 micro instance is typically down at the half to 1 cent level, which is about, from memory, about a sixth of the typical cost of acquiring those instances on demand. So if you're able to incorporate spot resources into your EMR clusters, they can have two effects. The first is they can obviously add additional compute resources that can accelerate the delivery of your jobs and therefore reduce the number of compute hours that you need to pay for overall. But secondly, they can also you can also add those resources at lower than normal cost. So you can see a worked example here of running a 4-node cluster for 14 hours, 50 cents per node would cost $28. Adding spot instances to that, which you acquire at lower cost than those on-demand nodes anyway, and it shortens down the length of time that's required to execute that task. You can reduce the cost of running that job to $22.75 in this particular example. So it's a great tool to use if you're using EMR to A, reduce the time that it takes you to execute your EMR flows, and B, also to reduce the cost of running those jobs. So really encourage you to take a look at the spot market. And it's very easy using the EMR console to integrate spot resources into your cluster, or even add spot resources to a cluster that's already running in order to bolster the amount of compute resource that it has and reduce the time that it takes to complete a task. So that's pretty much the content for the core part of the webinar. There's quite a few things as usual that we didn't cover today. So some other things that you might want to consider: dynamic creation of clusters for processing jobs. So all of these resources I've said are available through the API, through the SDKs that we provide, and also through the command line. So you can integrate cluster creation into scheduling tools that you might use or into other applications that you have, and dynamically create clusters to execute Hadoop processing jobs when you need them, and discard them when you don't. Obviously, the bulk of your data is stored in S3, so you've got a very low cost and very durable platform that you're going to keep your data in. The secondary benefit of that, of course, is it means that you're not paying for compute when you're not actually processing an EMR workflow. So store your data in S3 and keep it there. When you need your clusters, create them, pull your data down, process it, gather the results that you need, and then discard your compute cluster and just pay the low cost for storing your data. You can also further reduce costs for storage by using RRS or reduced redundancy storage for lower value or recreatable data. And if you don't need data permanently, then you can migrate it down to Glacier and pull it back, for example, for quarterly or annual processing. If you have processing tasks that you want to run very infrequently, that's definitely a technique that you can use. DynamoDB is a good tool for storing high-performance data, as we've already said. And you can integrate EMR with the VPC and with the IAM tools that we provide for improved network security. You can also use VPC for things like putting desktop workspaces environments close to your EMR cluster and get very good performance, for example, for JDBC connections into EMR if you're going to take advantage of that kind of technique using Hive, as I've already said. So lastly, additional resources. You can find quite a healthy stream of updates about EMR if you visit the AWS blog. Now, we recently moved the AWS blog, so it's no longer on TypePad. It now lives at the URL that you can see at the bottom of the screen there. Really advise you to follow the AWS blog. There's a lot of big data and EMR topics that are covered there, and you can also stay up to date with additions of new Hadoop ecosystem tools as we add them to the product. They'll typically be announced there, so that's a good place to go for extra resources. And you can also find some more good resources if you go to these two references. So there's a really good tutorial for EMR, which includes a lot of the tools that we've talked about today in a worked example to do with contextual advertising. If you visit the URL that's shown at the top of the screen here, you'll find that example of using Hive and EMR with one particular application use case. And we also have a really excellent series of YouTube videos which have been recorded and made available on the topic of big data generally and EMR specifically, which you can find if you visit the two URLs at the bottom of the screen there. The Elastic MapReduce Getting Started URL has links to all those video references and also links to a lot of documentation about EMR, which is obviously, probably get the sense from this webinar, a pretty expansive topic. We covered one of the ecosystem tools during the webinar today, but there's a host of others available, and you can find out a lot more about those if you visit the links that you can see on this slide here. So that pretty much concludes what we have for you today in terms of content. As usual, I'd just like to encourage you to follow us at AWS_UKI. You can stay up to date with our webinar program there. We've got upcoming webinars to do with storage and backup on AWS. And our next masterclass will be about using CloudFormation, one of our deployment tools for managing large numbers of AWS environments, or just making it possible for you to version control your AWS resources in the same way that you might version control the code base for your apps. So that'll be a good one upcoming in a month or so. And of course, you can find us at AWS Cloud as well if you want to stay up to date with global AWS news and announcements from around the world. So I'd just like to thank you for joining us today. We're not going to have a whole lot of time to cover a lot of questions because we've pretty much consumed the hour today, but we will definitely do question follow-up. So if you do have a question that hasn't been that hasn't been answered, that's been submitted, or you have a question that you've not yet submitted but you're interested in an answer to, I'll leave the webinar open for 5 or so minutes after the hour runs out with the social media slide up. And if you want to ask a question, please do so, and a member of our solutions architecture team will definitely get back to you with a response. We follow up on all questions. We had several hundred from the EC2 webinar that we ran recently, and we answered every single one of them within a couple of days. So if you do have a question, please answer it. We'll get back to you with the details that you're after. So thanks very much for joining us today. Much appreciated. And I hope to see you online for the next AWS webinar that we run here in Europe. Bye-bye.